In this video, we will discuss how to perform Rietveld refinement with known phases using XRD data. If you are interested in learning about the various aspects of Rietveld refinement and associated terminologies, I have already recorded an introductory video which you can find in the link above. Let's discuss the data. This is the sample XRD data in RAW extension which we have characterized. This is the instrument file used for subtracting the background in zero error. It is in the PRM extension. Even if we don't have this file, we can still proceed with the refinement process. These are the two possible phases included in our sample. They are represented by CIF files. Among them, we commonly observe the spinel phase and the rock salt phase. Since these phases are abundant, we will refine our data accordingly. So let's start with GSAS. I will begin with the GSAS software. This is the bash window that will run first and execute the GSAS Python code. Here, all the versions are listed. Now we have the data tree here, and this is the graph window. Now, the first thing we need to do is save our file. We will save the project, naming it XRD Rietveld Refinement. This file is essentially our GSAS project. So let's start by accessing the data. First, I will import it. Navigate to Import option and then select the powder data. Choose the GSAS powder data. You can either import it directly from here or choose to guess from the file format. Since it is a raw file, I will select this option. I know that it is this data, so I will proceed. Here is our sample data. Click here and it will prompt, is this the file you want? Do you want to read the file? I will confirm by selecting yes. So, instantly it has asked for the instrument parameter file and I have this file. Therefore, I will select this one. In case I do not have this file, then I can cancel this section. So I will select this one and open it. And now our XRD pattern is here. So, in this video, I will simplify the basics of this topic. It is very easy to do. Now I will navigate to the data section. The first thing I will address is the notebook, which contains information and controls. Inside the control section, I will focus on the maximum number of iterations, which is set to 10. We can increase this number, but let's keep it at 10 for a reasonable iteration. Then we will leave all other parameters unchanged. I will proceed to the sample. Here, once I access the sample, I will review the comments. I wouldn't need to take any action here. The range is from 16 to 99, covering the entire dataset. So I will leave this one without any change to it. When I come to the background, we use a Chebyshev polynomial and the refine option is selected. The polynomial order is set to 3, which is sufficient. Later on, we will incorporate some peaks originating from the background, but for now, we are leaving this aspect as it is. Next, I navigate to the instrument file. Inside the instrument file, the first step is to select Cobalt K alpha as my data source. I will leave all the other parameters unchanged. Next, I navigate to the sample parameters section. Inside this section, I have the option to input the instrument name. Although it is not necessary, it is crucial to ensure that the Bragg-Brentano configuration is selected. Additionally, I need to deselect the histogram scale factor option. This step is vital because we will be optimizing the structure with two known phases, each with different intensities. Therefore, it is necessary to untick this option as we do not want to scale the intensities equally. After that, the rest of the parameters will remain unchanged. Now it is time to import our phases. I navigate to the menu and select Import Phase from CIF file. The first phase I import is the spinel phase. I double-click on it. A prompt appears asking if I want to read this file, to which I respond yes. The name of the new phase appears and I confirm. It may take a moment to load. Then, a warning about a shift in origin pops up, asking if I want to shift the origin. I choose to keep the current coordinates and not to shift the origin. The GSAS then retains the current coordinates. Now, I need to link this histogram with the powder data. I will select this option and click OK. It has now introduced a phase here. Next, I will import another phase in the same manner. The other phase is the rock salt phase. It prompts to read the CIF file, to which I will respond yes. I will also need to link this phase with the powder data. Now both phases are incorporated here. Now I will click on a phase here, then under the data tab, there is the histogram sample raw file. I will select the phase fraction option. Currently it shows that 86.5% of this phase is present in the sample. Next, I will switch to the other phase and click on the phase fraction under the data tab, revealing that 13.5% is the contribution from this phase, the rock salt phase. With everything set up for the first refinement, I will proceed to calculate and then refine. Initiating the refinement process, the RW value obtained is 16.197. Since 16 is a satisfactory value, I will proceed to load the new results by selecting OK. Some of the peaks have been fitted here while others have not. Next, I will proceed to the phase tab. Inside the phase tab, under the general section, I will select the option to refine the unit cell. Currently, the latest constant reads as 8.092. Let's only take the refine option for this parameter. Then I will proceed to calculate and refine. The unit cell refinement process is underway and now it shows just below 16. After the unit cell has been refined, I will click OK to load the new results and then uncheck the refine option as it has been refined. Moving on to the other phase, its latest constant is 4.26. I will also select the option to refine this unit cell and proceed with the refinement process. And I will click OK. Upon refinement, the latest constant changes to 4.26539. The necessary refinements have been completed here as well. So I will untick this option. Now I want to navigate to the data tab, and within the data, I observe that there is 58% of the spinel phase and 42% of the rock salt phase. All this information is presented here. Additionally, when I check here, I see that the RW value representing the residual value is 14.693. Ideally, this value should be less than 10 for a satisfactory fitting or refinement. Now, as I review the peaks, I am not observing the COO and CO304 peaks assignment here. So what I will do is click on phases and then select sample. After that, I will click the home button on the graph window. So the phases peaks locations appear here. From this, I can clearly identify that this peaks belongs to the CO304 phase, the spinel phase, where this peak is from the background. Also, upon further examination, this peak doesn't correspond to either of the two phases, indicating it is from the background. Similarly, upon zooming in, we can distinguish that this peak is from the rock salt phase, while this one is from the spinel phase, and these others are from the background. In total, around 10 peaks are from the background. Hence, the optimal approach would be to subtract these peaks by fitting them as part of the background to achieve a better fit. So I navigate to the background and decide to subtract these peaks individually. First, I identify a peak originating from the background. I hover over it, and at the bottom of the window I see its location, where I am going to subtract or fit into the background. Instead of outright removing it, I choose to fit it as part of the background. This particular peak is located around 19.98 with an intensity of approximately 2000. I will slightly increase its intensity for a better fit, let's say around 3000. Initially, I will refine only the intensity, leaving the peak's location unchanged, and I wouldn't refine the sigma since its impact is minor. However, gamma is crucial, so I will refine it. I start with a default value of 8 for gamma and refine it accordingly. After refining the intensity and gamma, I load the new results. Next, I refine the peak's position. and after the refinement, I untick this option. Now, I will add another peak, which is essentially this one, a part of the background. Its location is approximately 32.9. Let me assign a high intensity to this peak and refine its parameters. I will set gamma to 8 and refine it too. Now when I refine, I notice the intensity has shifted a bit, but it is decreased here. Let me load the new results. Next, I will refine the peak location. After refining, I see the intensity has shifted further. I will decrease it to 6000, recalculate and refine. Now it's positioned correctly, but the intensity is still too high. I need to focus on this. I will try reducing it to 5000 and refine again. Now it looks fine and the intensity has decreased. So I will click OK. Now when I look at this one, it is part of this one. However, when I examine it here, it is part of our calculated spectrum. These two peaks are from the background. I will select another peak and another peak here overall. These two peaks are from the background, so I will consider this peak first. Its location is 38.45 and its intensity is around 3000, so I will write 6000. Here, this is 8 as usual. I will refine this one as well, and I see that it has reduced and merged here. Then I will refine its position as well. I see that this is fine, but the intensity is not. So I will increase its intensity and refine it. Refine, and we have reached 13. Here I see that it has fitted this peak instead of the other one. This one is fine, no problem. We will add another one, which is the fourth peak. I will set its location to 38.4 and its intensity to around 6000 and refine this one. Here I will set 8 and refine this one as well. Now I see it has refined this one as well, and we have just gone under 13. So this is fine. Now when I look here, I see a very small peak here, so we can ignore this one. If I go here toward this one, I can see that these are the calculated patterns, but this one is the pattern from the background. The fifth peak is at 44.65 with an intensity around 8000, and we need to refine this one. Similarly, this one is at 8 and we need to refine it as well, so I calculate and refine. I see that it has fitted very well and I have reduced it to under 12 here. Now as usual, I proceed with the position refinement. Although the position is already very refined, I can further improve it. So it has changed slightly and improved. So now I have this peak from the background. I can check here and here, and then the phases appear here. This is the phase present here, but this one is not. I can see that this one is a calculated pattern, but this one is not. So its location is roughly 47.24. I add another peak at 47.24 and the intensity is around 4000. One thing I can do, just as I have refined these peaks, is that no further refinement is required, and again stop them from refining further. So this one is going to be refined here and it is here. So I go and refine and it is refined. We have gone under 12, but the intensity is not. Let me refine the position. So it has refined the position and there is a very good fit here. Now let me get rid of this refinement as well. Now if I look here, these are the calculated peaks. This one is again from the background. It is located at 58.82 with an intensity around 2000. I will set this value to 8 and then refine it. It has been refined, so I will refine its position as well. It has been successfully refined and here I have completed this step. This peak is not part of the background. I can see that these other peaks are part of the background and peak around 62.7 has an intensity of about 2000, so I will write 4000 and here I will write 8. Now I will refine this peak, refine this one and proceed to refine. Finally, I will refine its location and its location is now refined. I need to add another peak here. Peak 9 correspond to this one 865 with an intensity around 2000. So I will note down 4000 here. Now it seems to have fitted quite well. No further refinement is necessary. Now if I look here, we are almost finished except for this peak, which is around 69. So this is the final peak we are addressing, and it is approximately at 69. Its intensity is about 4000 and its width is 8. So we have refined it and now it is perfect. We are on the right track. Thus we have refined a total of 10 peaks. Now it is time to examine the calculated peaks. If I take a look here, the peak doesn't fit very well. Similarly, if I move to another calculated peak, I can observe that this one also doesn't fit very well. I can observe that this one also doesn't fit well. So the issue seems to be with the peak width. Moving on, let's see here. I can notice that it fits, but not very well. Similarly, when I examine this one, the peak width doesn't seem to be fitting properly. Now let's proceed similarly. If I examine this area, it is also not fitting well, showing two peaks instead of one. Furthermore, over here, there seems to be a different structure. Let's concentrate on our primary peak here. This peak is significant and we need to refine it now. Thus far, we need to examine the instrument parameters as they might contribute to both sample broadening and instrument effects. Inside the instrument, we have the U parameter with a value of 1, which plays a role. We will begin by refining this parameter, select it, then proceed to calculate and refine. I can see that the refinement has now reached 4.8, indicating a very thorough refinement. Similarly, if I now move towards the last peak here, which were quite distinct previously, now they are fitting very well. Now we can refine the other parameters as well. We will not refine parameter V because its contribution is minimal, but we will refine parameter W. Let's also refine this one. Although its contribution is very slight, so not to a significant extent, thus there is no need to refine this one. Now at this point we are here. Our refinement is nearly complete. I can observe that the other peaks are fitting very well. This indicates that our fitting process is complete. As our RW value has dropped below 5, which is excellent. We have contributions from the two phases, the spinel phase and the rock salt phase. Similarly, when I turn to the phase fraction, in order to determine it, I observe that 59.4% represents the spinel phase, while 40.6% originates from the rock salt phase. So we have completed this refinement. Furthermore, we can delve deeper into refining aspects such as the crystallite size. I am noticing that there is not much difference occurring here, and the crystallite size has changed slightly. Similarly, I can adjust the microstrain, and now I see there has been a slight change, but not significant since we are already within optimized parameters. The component that previously had the maximum contribution has shifted slightly. Now when I select this one and refine it, there is a little change happening and the size is now 10. As for the microstrain, there is a slight alteration here, but our ultimate value remains at 4.7. And with that, our refinement is complete. Here, we can observe the index peak list, the unit cell, and then the reflection list. All of these represent the reflections. For instance, the 111 reflection is located at position 22, and then we have this one. We can see that it is now displaying the reflections, so we are nearly finished here. As the length of this video has increased, I will stop here. In the next video, we will resume from this point. Remember to save your project file. Thanks for watching the video.